And I will explain what is actually decision tree doing. And here is some decision tree that is actually doing with the numerical values of attributes. And if we plot the data in 2 dimensions, this tree is actually selecting data into cubes and circles. And we can see that the first is decision, this line, whether the data has value lower than 2. If it's lower than 2, then the next is checking if epsilon value is higher than 2.5. If it's higher than 2.5 and lower than 2.6 is circle, otherwise it's a square, not cube. And if it's higher than this line, higher than 2, then it's selecting again, making decision boundaries in this space regarding category of the circles and squares. Here I would like you to remember 2 things. First, here we have actually classification tree is learning this separation of space, and this is called a decision boundary. The second important thing is that here we are isolating one solo point which is overfitting to the data, and here I have the better tree which is smaller, which is not isolating. It's making mistake here, but it's deciding with we have smaller tree that is deciding that everything that has value lower than 2 is a square and not a circle, and it's making one mistake here, but we can live with it. This is when we will not have 100% of the items correctly classified in the tree. This is this situation where we have 66.7 correctly classified, others will not be correctly classified, and so on. Maybe it's better to see it this way. Second thing, here actually all these classification models are learning these decision boundaries, and decision tree are learning the most primitive one. You can see here that actually decision tree is learning uh, really, let's say, not really sophisticated boundary. Neural networks can learn much more sophisticated boundaries. And something that I personally really like a lot is a random forest, which is actually one advanced variation of training lot of decision trees. We will go that during the next lecture, and you can see that this boundary here is actually really nice because algorithm is learning the boundary around separation of each and every data point. Uh, this is not important to know, but I think that this clarification is important to understand what we are doing with the classification trees. Do you need any clarification more, or so far so good, you are catching everything?
So far, so good.
Thank you. If you are catching, because last time you had so much problems with understanding some basic concept, that I'm really proud of you that you can follow this time. So be proud of yourself as well, right?
Thank you.
Sashka. Sashka, you are doing okay as well. Now, if you complain about something that is not clear, I will explain it further. Otherwise, I will go on. So next classification model is naive Bayes classifier, which is really good for binary classification. And I will not go into details, but here actually we can learn to classify into like or dislike binary categories. What is the problem? Problem is that naive Bayes can actually model some probabilities, and these probabilities can be actually assumed to be distributed by the Bernoulli multinomial or Gaussian distribution. I'm usually using the multinomial variant because it works well for the text. Uh, it was not covered. It was not covered in the tutorial. Okay, now I was too quick because I haven't tried. Okay, maybe not on this data set, which I don't have a clue what is inside. Let's go to the zoo. This one we all understand. Actually, I will select the iris data set because it's too many classes here. Okay, actually, what we are seeing is evaluation of the results. I will cover this later, but naive Bayes trained the model that is differentiating iris setosa, iris versicolor, but is making some mistakes. Sometimes instead of iris versicolor is thinking that is iris virginica, and sometimes when it should be iris virginica is thinking that is iris versicolor. And we can see the tree. I need to connect it again, I think. So finally we have a classification tree that is capable of really good separation of iris setosa, and sometimes is also good in iris virginica, 97% correctly, iris versicolor 98%, and it's making petal width. When it's petal width higher than 1.5, the model is confused. That's how classification tree is doing. And the trained naive bias is actually doing the same thing, confusing between iris virginica and iris versicolor. I think that. So what I have done now, I have to this evaluation, which is called confusion matrix, connected naive bias classifier and my classification tree. Classification tree is making uh, several mistakes, 2 mistakes here, 15 mistakes here, and 18 mistakes here. And naive bias is actually making more mistakes, but only between two classes. So we trained two different classification models, and one of them is actually performing better. I will try to train the third one. And we can see how is logistic regression doing. Actually, logistic regression is doing the best job. It's making mistake only in 10 and 11 cases. I will now go back to the naive bias classifier. Why is naive? Naive is because it's assuming that there is actually here I didn't perform well this experiment because I used the training data for testing. I should be actually dividing the data set and using only the test part of the data set for the evaluation, which means that I don't have, my experiment was not correct, but I just wanted to show you that different methods are performing differently. And this is something that you should also consider in your seminar for the classification task. I'm suggesting that you train the classification tree, which is actually good because you can visualize it. You can train the naive bias classifier, as I did, and train logistic regression. And also, you can train the random forest. And we will quickly check how random forest is doing. If you check, logistic regression is making 11 and 10 mistakes, and random forest is making 9 and 13. It's not really clear which one is doing better. So here we can even check the data. Just a moment, maybe I can show you like this. So let's say I'm in naive bias and I'm checking which 22 datas were incorrectly select, and here I have the list of these 22 rows in the data set that were really iris versicolor, and naive bias classifier decided that they were iris virginica, which means that we are looking only into the mistakes. And if I select this one, we can see that naive bias wrongly assumed they are versicolor, but in reality they were virginica. So I think naive bias is something that you can also check. But remember, when you divide your data set, that's the beginning, into the training and testing set, naive bias is assuming that these two data sets are independent and they both do have the same distribution. And this is naive assumption, so this is why it's called naive bias. And maybe one. Uh, what is naive bias trying to learn? Naive bias is actually, when it's binary classification, assuming that each class of the data has different distribution, and naive bias is actually trying to find boundary where these two distribution can be separated. And if you see, here is the line in the middle where naive bias is deciding, okay, here is the cutoff, but some items of this distribution here are left on the right side and some are left on the left side. And this is the mistake that we are actually seeing in this confusion matrix. So naive bias is actually making this naive assumption. It's working really nice, but sometimes these distributions cannot be well separated. And then in this intersection, naive bias is making a problem. Still, it's very fast, working really nice. I'm using a lot of naive bias classifier as the baseline classification to test whether other models are overperforming, are doing better than naive bias. And now I will go to the evaluation part, which I have already shown you. So first we said that we will measure accuracy, how many correct classification out of the total number of test cases we have. But later I showed you something that is called confusion matrix. So this is confusion matrix in orange. And how do you read it? Here I have hypothesis that is model doing, and I have the actual label of the data. And when model is selecting the data in the positive class and the true label of the data is positive class, we call that true positive. When the model is selecting as true negatives and the true label is negative, we are dealing with true negatives. And these two greens are actually all correct, while we classified the truly positive data as positive and truly negative data as negative. But model is making problems in these false negative and false negative categories. False positive is meaning that the algorithm is thinking that something is positive while it's being negative, and here algorithms is deciding that something is negative while it's been positive. And these two kinds of errors uh, have different severity in the problems that we are solving. Let's say like this: if I have some medical examination and the model is predicting, let's say it's breast cancer, to be a really dramatic case. So model is selecting patient with positive breast cancer as negative, and model is selecting the negative breast cancer as positive case. Which one do you think in this use case is the worst error? On which error should we pay more attention? What do you think? Once again, for breast cancer, is it more severe error that I do have a cancer and model is predicting that I don't have it? Or is a worse situation that I don't have a cancer, but model is predicting that I have a cancer? What do you think?
I think the second thing you said is better than the first thing
Yeah.
because if you have
Okay.
cancer and your model say you don't have, we will do nothing against the cancer.
Yeah. That's correct. So this was the second is like false alarm. Okay, I will be a little bit upset, but then I will be relieved, everything is okay. And the first situation can be life threatening because I didn't get the proper treatment. But there are other cases where the opposite situation is preferred. So this is really not generalization. Sometimes it's better to have more false positives, and sometimes if you prefer decide between two algorithms, it's not one rule. You should decide regarding the content of your data. Sometimes you prefer more false negatives, sometimes you prefer more false positives, which is returning here. So naive Bayes is making these two mistakes. Classification tree is making mistakes in three classes. Logistic regression is making these two separate but lower than naive Bayes. And random forest is making pretty much the same as logistic regression. Here is a little bit higher and here is little bit lower. And if I looked into this classification, I would probably go for random forest when I see these results, but logistic regression is doing really as good as the random forest when I only look into these two results. Is that clear? So you will also need to evaluate your model. And the last actually explanation is like this. This is actually just another visualization what we have discussed here. So let's say that this blue dot is actually model. Model is doing some mistakes because it's selecting as positive some negatives. These are all positive, but it's missing to select as positive some really positives. These are false negatives. And we can calculate how good model is doing from these values. And these values are called precision and recall. But here I have one problem because it's overlapped. And this is explanation for the document classification task, but actually can be on any data. Precision is how much data we actually classified as positive and how much of this was really positive. And the second one is how many of the documents was returned and how much was out. Okay, one is how much of the positive examples were selected out of all positive examples, and sometimes is what you have returned, how good that was covering the positive examples. uh, how many of the positives you are returning is recall, and how precisely you are returning is precision. So you will have this precision and recall as evaluation metrics also in the tutorials. And I want you to notice that precision and recall can be calculated from this matrix as well. This is related. So precision is true positive divided by true positives plus false positive, and recall is true positive divided by true positives plus false negatives. And finally, so one is how much of the relevant data we are capturing with the model, and the other one is how precisely is what we are capturing. And we would like to have some metrics or evaluation measure that is capturing both, which means that F1 score is harmonic mean of precision and recall. And I will not go into receiver operator characteristic curve because I think it's going to be too much. So remember, I want you to remember to know confusion matrix because you will need it for your seminars. I want you to understand the concept of precision, recall, F1 score, and accuracy. Accuracy we are not using much because accuracy is known to be bad measure. It's not showing, it's not proper technical evaluation measure, although it's intuitively really easy to understand. But we prefer to have the confusion metrics because it's much more telling about how good the model is doing. And I think this was really nicely explained in tutorials, but I will cover shortly also this clustering method. Clustering is actually unsupervised method that is trying to find similar groups of the data. And we don't have a data class in advance. Number of clusters is also not known in advance, which means that we can search for the best number of clusters, and actually we are trying to find clusters that are as much as possible apart from each other, that intercluster distance is maximized, and we want elements of the cluster to be as close together, which means the distance within cluster is minimized. Now I will clean everything. I closed and all add-ons were uninstalled, but I think this one will go fast. So this educational add-on, you maybe it was already included in the tutorials, but it's really good because it explains how some of the algorithms are doing. In the meantime, I will go to my presentation and start talking about algorithm. So here I have the visualization. In this algorithm, I'm trying to find 5 groups. In the first step, I'm randomly assigning the centroids of this I think orange will restart automatically. Okay. So randomly positioned in this space X centers of the clusters. Then I'm trying to assign the closest points to these clusters. And then when I have the closest points, the closest data to the cluster, I'm recalculating the new cross position to be much better centered in this data that was the closest. And then I repeat this procedure by calculating the which data points are the closest and repositioning the center of the group, and I end up if 5 groups where I have the center of this cluster. And this is the typical customer segmentation algorithm. And before we go to the orange, I want you to understand this. If I start training this algorithm with initial seeds on these 2 positions, this algorithm will decide that it has 2 clusters, one upper and one lower, and will do the bad clustering because it's heavily depending on the position of initial random position of the centroid, which means that we should repeat calculation of clusters several times with the random initial positioning of the center. Second problem that we have, so this is the correct. In the second try, random positioning was better, and then algorithm decided that these 2 clusters are correct. The second problem is outlier. Remember, I said that outliers we are clipping down to some value, because if outlier has some really large value, then when we calculate distance, this center is really pulled toward the value of outlier, which means Cummins algorithm is really sensitive to outliers, because outlier we cause separation is these 2 groups, which is not correct, which means that first we need to detect outlier and then omit this outlier in the further clustering. And the third problem is that Cummins is not capable of selecting this nested or elliptical data. It will always divide these 2 groups, while neural networks are actually capable of selecting these 2 clusters. The second clustering type is hierarchical clustering that is producing this, let's so-called diagram that is called dendrogram, and it's read like this. First and second cluster are the closest together. Then, and I think these six represent that six items are in these two clusters together. Then the third cluster is the closest, and we have, oh, I don't know, I don't recall what is the number here. I was thinking that it's adding up. It's not. Uh, then it's third that is connected with this one, and we have in the other branch fourth and fifth cluster that are closest together, and they are all joined together in one huge cluster. Clustering can be doing bottom up. So I start with all data, try to divide them into clusters, or can be bottom up, where I start with one data item, calculate which one is the closest, and put these two items in one cluster together. So one is agglomerative, which is bottom up by from the bottom level. It's merging and merging cluster until I have all the data in the cluster. And divisive or top-down clustering is actually splitting the whole data into two parts until it cannot separate data anymore. And I think that this visualization is a really good one. So here I have a dendrogram, and this dendrogram is saying that points 1 and 2 are together, and this is one cluster. Then point 3 is added to cluster number 3. Points 4 and 5 are in cluster number 2, and they all together form cluster number 4. Which brings me to this picture. Here I have clusters, cluster number probably in and how can I measure the distance between cluster is there are really several methods. This one is that I'm measuring the distance between two closest points. This one is I'm measuring the distance between two clusters between two further points. And I can measure the distance that I'm measuring the distance between all points in one cluster to all points in other cluster. And this is pretty much it. And the final is that I am measuring the distance between centroids. And this is variations of the distance. Distance can be calculated several ways that is also implemented in Orange. It can be Euclidean, Manhattan distance, or Chebyshev distance, and so on and so forth. I will try to Google. Okay, this one will serve. So Euclidean distance is actually distance between two vectors. Manhattan or city block distance is actually how much points we need to go right and then down. Chebyshev distance is actually just projecting to the distance on the axis, and Bikonsky distance is little bit complicated. I also we use a lot of cosine distances, which is actually Euclidean distance is sensitive to the size of the vector. If one of these vector is very big, then the distance can be distorted. So instead, we are very much calculating the angle between vectors as the distance. So this is called the cosine distance. Okay, I will stop here. Let us try to do some clustering. Okay, iris, maybe zoo dataset for a change. But now I will use these interactive comments. Something is not working with this education because I wanted to show you how the algorithm is working. But now I just have comments and so I have actually used the zoo dataset, which we know that is a labeled dataset, but I'm just using it as example because this dataset I think is clear for everyone. This, maybe I can have this scatter plot. Oh, this scatter plot is not doing well. Box plot is better. So here I have the box plot, and box plot is saying that in cluster 1 they are all pink animals, which means cluster 1 is pure mammals. Cluster 5 is birds, but there are some reptiles included. Insects are mixed with intervertebra, and this intervertebra cluster is clear. And my what else come means I can use the fixed number or I can use the from to, where the orange is calculating the silhouette score, and when this silhouette score is biggest, come means in orange is actually with this biggest silhouette score predicting how many clusters do we have in the data. So for this data set, orange thinks that we have 5 clusters, although we know that, let me see, what do we have? with 6 clusters. With 6 clusters, I'm confusing fish with mammal and reptile. Mammal okay, invertebrate okay, birds and amphibian and reptiles are together. 6 looks little bit better as the classification. 7, 1, 2, 3 clean classes, 4 clean classes, and 3 mixed classes. And this one is with 7. Okay. Do you have any question? I think this with orange is clear because you all watched the tutorials. If you haven't watched, this would be too fast. And I really appreciate that you have